My name is Annika Thomas, and I study collaborative visual intelligence, which will be one of the key technologies to enable multi-robot autonomy. We're going to be seeing a lot of multi-robot teams in the next few years. We're going to be seeing warehouse robotics, teams of robots packing boxes. They'll be alleviating some of those physical stresses from our factory workers. We're going to be seeing robots in industrial kitchens and hopefully around the house. We're going to be seeing teams of robots that will go out and help us map settings in natural disaster scenarios. Forest fires help us allocate those resources. And one of my favorites, we're going to be seeing robots on other planets and on the moon, helping us map the environment, collect samples in these extreme environments, places that humans can't go. So why don't we have these technologies yet? Well, one of the key enablers of this is happening under the surface, in the brains of our robots. It's in the vision and perception side of things. And this is where my work comes in. A lot of our robots aren't necessarily interested in what the other ones have to say. They have their own tasks that are pre-programmed, and they basically ignore one another. But I want our robots to be interested in what each other has to say. And in order to enable these multi-robot technologies, I believe that our robots have to intelligently understand the world and to be able to think collectively in order to collaborate. Now, what does it look like to see as a robot? Well, let's take that forest mapping, natural disaster scenario example. So this is a flight taken from a drone, and in order to map this area, the drone has to figure out where it is. So in my research, we use spatial artificial intelligence in order to extract the locations of trees. We're basically creating this geometric map of the environment that's based on the structure of the environment. And this enables our robots to localize, to share their maps and align them in cases where this environment begins to look quite different too. So this is the setting of long-term localization. The maps that our robots are creating are ones that can be shared and understood across all of these different settings. So this is our aerial case. We can also apply this technology on the ground view case as well. And the ground view case is especially complex because when our robots come to the same place from different viewpoints, the area begins to look very different. But when we use this kind of mapping approach that has to do with the underlying structure of the environment, they're now able to understand those maps that they share with one another. So you can see here on the bottom, these are the maps, the object-based maps that our robots are creating and sharing with one another. We're actually embedding language into these maps as well so that our robots can share important information. But these aren't necessarily maps that you or I could understand. So what if we want our maps to be those that humans in the loop, people that don't have a PhD in robotics, are also able to understand? So the state of the art for this kind of mapping is to use points or features in the map to create these environment representations. These are kind of like the IIA instructions of building a map. If you squint, you can kind of start to understand what it looks like, but it's not that user-friendly. When we begin to add color to these points, it's something that you or I can understand a bit more, but there still isn't much substance to these maps. So people invented this process called voxelization. We're familiar with 2D pixels, these are squares. 3D voxels are basically extracting those and turning them into 3D models as well. So if we apply these to a map, then we begin to get a little bit more substance to the map. But it's still something that's a bit difficult for you or I to understand. You can kind of see the desk in the middle of this, but it's still a little bit difficult to understand. So about 5 years ago, there was a paradigm shift in the world of 3D reconstruction when these things called neural radiance fields came out. So these basically make these photorealistic 3D environment representations that you or I are pre-programmed to understand. The only problem is when you try and put this on board a robot, you might melt your GPU trying to render the image. So a couple years ago, another method for this to make these 3D photorealistic environment representations came out called Gaussian splatting. And this is what I use in my research in order to create photorealistic 3D worldviews. We're basically representing the environment as hundreds of thousands of these fuzzy balls, these colored Gaussian, 3D Gaussian distributions. And the cool thing about this type of environment representation is that we can render it in real time. So basically, we can move around the environment and understand and look at things in real time on board a robot. So what I'm doing in my research is I'm actually expanding this beyond these indoor room settings in these small environments to large outdoor settings as well. And this is taken here on MIT's campus. We're also reducing the fidelity of these maps so that they're still able to be understood by you or me, but there's something that a robot could run on board. So we're really traversing that bridge towards embodied AI. So if I can leave you with anything here, we're going to be seeing a lot of different multi-robot teams in the next few years. But in order for these robots to actually fuse their maps, to get that hive mind, in order for our robots to work together, they first have to learn to see together. Thank you.
So Annika, this is fabulous technology. My question to you is, when you look at this, the applications, most people think of the military warfare. Where are the ethics around this? Where do you draw the line in terms of this being hijacked and being used for something counterintuitive?
Yeah, I mean, I definitely think this type of technology is going to be, helping our national security, our national defense. But I see the types of applications in robotics as stretching much further than that, especially in the next few years. We're going to be seeing humanoids just around us in the next 10 years, doing things hopefully like our dishes, hopefully things like alleviating some of those physical stresses in warehouse robotics, making smarter factories, making those logistical decisions in real time in order to alleviate some of those stresses, some of those potential workplace accidents. I think that it's a paradigm shift towards a smoother way of life in a way that's going to help us.
So do you agree with Elon Musk in terms of having a robot in everyone's house in the next 10 years, maybe 2, 3?
If we're already seeing Roombas, those are technically robots. So I think I'd like to see that. I'd love to see a robot that does my dishes and not my creative, artistic homework. But yeah, we'll be seeing a lot more of it.
Fabulous. Any questions from the audience? I guess not. Great. Thanks a billion. Thank you.